Hello to our friends joining us via recording. This is the last part of lesson number 9 about the muscular system. We actually covered almost all of this material, so there's just a little bit of information left. Want to make sure we cover that to get all on the same page. Friendly reminder, hopefully you saw it in the announcement, that these assignments, there are two halves to lesson number 9. Both assignments, both halves of the lesson number 9 assignment are due by Sunday. So if you haven't already, we should definitely get part 1 knocked out ASAP. We need to make sure we've knocked out part 2 by Sunday. So let's remind ourselves a little bit exactly where we left off. The very last thing that we were talking about at the end of yesterday's class is we were talking about sarin gas and we were talking about Botox. For my friends who are here in class with me right now, help me out in the chat. Did we decide that sarin was a problem with too much acetylcholine or too little acetylcholine? Is sarin too much or too little acetylcholine? Yeah, exactly. Sarin gas is a problem with too much acetylcholine. So I'll circle our answer here, too much. Now, let's remind ourselves though, when I say that sarin is a problem with too much acetylcholine, it's not that my motor neurons are making too much, right? That's actually a question on the homework assignment, a true-false question. When we talk about sarin gas, this is not an issue with those motor neurons spitting out too much of the message. I have too much message because, like I see in the chat here, we've got some issues with my enzyme called acetylcholine esterase. Acetylcholine esterase, or I'm going to abbreviate it for you, ACHE, acetylcholine esterase. When acetylcholine esterase is doing its normal job, what is the normal job of this enzyme? What does it normally do for our muscle cells? Yeah, several of us are chiming in correctly. The job of this enzyme here, its normal job when it's doing what it's supposed to, this breaks down acetylcholine. So, and by the way, if abbreviations mix you up a little bit, wouldn't hurt when you're taking your notes or when you're reading stuff to actually write out the whole name. I will give you on the assignments and on the exam, I'll give you the abbreviation and the name. Acetylcholine is the message that neurons use to talk to muscle fibers. Acetylcholine esterase is the enzyme that we find in the membrane of a muscle cell that breaks down acetylcholine. Because see, here's the deal. Anytime I have acetylcholine, remember from our flow chart from yesterday, acetylcholine goes, it attaches to those chemically gated sodium channels. In rushes the sodium. Eventually, that's going to help us make that action potential that helps us to spit out our calcium, makes us do muscle contraction. Anytime I've got acetylcholine, my muscle is going to contract. So if a neuron spits out acetylcholine right now, you're going to contract right now. But you don't want to contract for that message again in about 5 minutes. You want to contract because of the message when you hear the message, not when we hear the echo of the message 20 times. So the job of acetylcholine esterase, ACHE, for us bad typers, right? The job of this enzyme is basically to make sure we don't have echoes. We heard the message once, acetylcholine. We don't want to hear it again. So as soon as a muscle cell contracts because of acetylcholine, it breaks down that acetylcholine, no more message, no more contraction. Now, with sarin gas, we said this is an issue with acetylcholine esterase, my enzyme. Is my enzyme working too hard or not working hard enough? What's happening with sarin gas and this enzyme? Is it working too hard or not hard enough? Yeah, so ACHE is not working hard enough. When someone is exposed to sarin gas deactivates acetylcholinesterase. Now, I should mention, because you have some more true-false questions about this, when sarin gas deactivates acetylcholinesterase, it is, like Kira mentioned, it is temporary. It's not permanently deactivated. It's not always going to be shut down. For as long as sarin is attached to the enzyme, it can't do its job anymore. But it will eventually leave the enzyme alone. You will go back to being able to chop up those messages eventually. So exposure to sarin gas is not always fatal because we can actually reduce the amount of sarin that's attached to our enzymes. So it's not, when you're looking at your statements about sarin gas, we don't permanently deactivate this enzyme. We just deactivate it for a while. When sarin gas attaches to it, it's not working. It's not breaking down acetylcholine. So big picture, sarin gas. This is an issue with having too much acetylcholine at the neuromuscular junction. The reason I've got too much there is because I'm not breaking it down like I'm supposed to. So think of that as an echo. Like I said, we hear the same message too many times, respond to it every single time. That's the problem with sarin gas. When we talk about Botox, was Botox an issue with too much or too little acetylcholine? What was going on with Botox? Yeah, exactly. Botox is the opposite end of the spectrum here. So Botox is an issue with too little acetylcholine. When I talk about having too little acetylcholine at the neuromuscular junction, why don't I have enough? What's happening to make it so that I don't have enough acetylcholine? Do we remember? Yeah, so this time, when we talk about Botox, Botox is an issue with the neurons. So when someone is exposed to Botox, there's too little acetylcholine at the neuromuscular junction because the motor neurons can't release it. The motor neurons can't release it. The motor neurons can't release acetylcholine because remember from our picture, the botulinum toxin, Botox, goes inside these neurons and then it chops up those proteins that help it to spit out acetylcholine. So if I've chopped up those proteins, I can't spit out acetylcholine. If I don't spit it out, I can't start the process of muscle contraction. So with Botox, we have no muscle contraction because there's not enough acetylcholine. With sarin gas, we have way too much muscle contraction because that's an issue with having too many messages. We can't chop up our message from 5 minutes ago and we've gotten 10 messages since then. Our muscles are going nuts. They are spasming. I had seen the question in the chat for how permanent Botox is. Anyone who gets Botox would tell you it's not nearly permanent enough. It's something, I want to guess, something like 2 to 4 months or something. It's kind of as long as it takes your body to rebuild those proteins. So Botox goes in and chops up the proteins. Here, let's go back a couple of slides and look at them. Botox goes through and chops up these proteins here and this protein as well. So until your body goes through and remakes those proteins, Botox is working. But once your body rebuilds the proteins, then we're going to be able to release muscles again. Then those wrinkles are going to come back to haunt you. So Botox is also not permanent. It's a little longer lasting than a typical sarin exposure might be, but it's definitely not permanent. Yeah, thanks to the central dogma, right? There's unit number 2 back to haunt us, central dogma. So rebuild those proteins and you'll be able to send messages like nobody's business. So we ended with the meme, right, that Dr. Aulis made for you. Remember, Botox is the most toxic thing known to man. And again, we like to put it in our faces. So fun times, fun times. I bet you'll talk about it more in your microbiology class. So stay tuned for microbiology. I suspect we'll talk a little more about Botox maybe. The last thing we're going to talk about today are the 3 types of skeletal muscle tissue that you have in your body. And if you haven't worked this far in the lesson yet, you're probably like, what in the world? We've got lumberjacks. Like, what are we talking about? So I'm going to use a couple of analogies to help you see how lumberjacks and see how forests versus wood piles help us understand the way that your muscles work using these analogies. Before we start talking specifically about the analogy, let's talk about the 3 types of skeletal muscle tissue. The 3 types of skeletal muscle tissue. So the first type of skeletal muscle tissue we have is what's called fast glycolytic muscle. Fast glycolytic skeletal muscle tissue. Second type we have is fast oxidative skeletal muscle tissue, fast oxidative. And the third type we have is what's called slow oxidative muscle tissue. Oops, slow oxidative. Let's add a little line, RL. 3 types of skeletal muscle tissue that you have in your body. And everybody's skeletal muscle has all 3 of these types of muscle in them. The amount that you have of each actually varies from person to person. And when you do different kinds of exercises, you can encourage different types of muscle tissue to form. The names of these muscle tissues tell us a whole lot about the way that they work. So let's start with the word that's represented by our lumberjacks here. So the word that our lumberjacks is helping us to understand is this first word in their names. So the first word in their names, each of our muscle tissues is either a fast type of muscle tissue or a slow type of muscle tissue. How this relates to lumberjacks is consider that we've got some firewood or a log in the backyard at a cabin, and we have 2 types of lumberjacks here. So we've got the professional lumberjack over here on the left, and then we've kind of got the amateur lumberjack who just does it for fun on the weekends, but hey, he does love anatomy, right? Check out that little skull hat. So this is the anatomy version of a lumberjack versus a professional lumberjack. If we were to give both of these lumberjacks this amount of wood and tell them to chop it, this lumberjack is going to chop through it super quickly, super efficiently. This one, maybe not so much. Chop up 1 log, get some lemonade, sit down for a little bit, take a picture and post it on Instagram, right? Because he's got his Instagram-worthy outfit going on. So we would call this friend over here, this is going to be an example of our slow types of muscle tissue, whereas over here on the left, we've got our fast types of muscle tissue. When we talk about slow versus fast, we're talking about how quickly a muscle cell can use energy. Do you happen to remember the name of the chemical energy that cells have inside of them? All of our cells use it. I call it energy money, if you will. What's our energy money in all your cells of the body? Yeah, exactly. So my energy money is ATP. ATP. When we're thinking about muscle tissue and the way that muscle tissue contracts, it's always going to get its energy from ATP. So some of our types of muscle tissue break down ATP really quickly. We'd say that they have what's called a fast ATPase. That's an enzyme whose one job in life is to chop up ATP. So if you are a type of muscle tissue that has a fast ATPase, you can chop up ATP really quickly and get the energy from it really fast. If you're like my friend over here, my Instagram lumberjack, who chops things a little bit more slowly, you're still going to break down the ATP, you're still going to get energy from it, but you're going to do it more slowly, like its name suggests. When we talk about a fast ATPase versus a slow ATPase, the biggest information you can get from this part of its name by itself is how strong your muscle contraction is going to be. So in other words, if I'm trying to heat up my house, I've got this firewood and I want my house to heat up, I need to get all of this into small enough pieces to fit inside my stove, inside my house. My fast ATPase, my professional lumberjack, he's going to chop up that wood in no time at all, and my house is going to get hot really quickly, or the amount of heat that he's going to generate for me is a lot. When you look at a type of muscle tissue that has the word fast as its first word, when we talk about a fast type of muscle tissue, that's going to mean that we have really strong contractions. So my fast glycolytic muscle tissue, that's going to be a really strong type of contraction. Or a fast oxidative type of muscle tissue, that's also going to be a really strong contraction because it's chopping up ATP really quickly. The energy in the ATP is available right away. Compare that to my slow lumberjack over here. Eventually, he's going to chop through all this wood too. Eventually, I will get warm as well, but it's going to take me a lot longer to heat up the house. The amount of heat that he's generating for me is not quite as much. So when we talk about slow oxidative muscle tissue, this is going to be a weaker contraction, So if we're looking at our three types of muscle tissue in your body, if you just look at their first name, if you will, fast or slow, that's going to tell you how strong of a contraction those types of muscle tissues can give you. That's our first part of their name. The second part of their name has to do with the way that they make their ATP. So let me make my list again. We had fast glycolytic, we had fast oxidative, and we had slow oxidative. We just talked about what this fast and slow means. It's essentially how strong of a contraction we can do. Now we need, in the second part of the names of these types of muscle tissue, now we need to figure out how much ATP they have around. We're going to chop through that ATP. Now we need to figure out, do we have a lot of ATP or do we have a little bit of ATP? One of my types of muscle tissue is called glycolytic. And when we talk about glycolytic muscle tissue, does anyone happen to remember what molecule this type of muscle tissue uses to build its ATP? What do I use to build ATP if I'm glycolytic? Yeah, there we go. So Kira's mentioning for us, we use the molecule glucose in its simplest form. The way that your muscle cells like to store glucose is in the form of something called glycogen. So remember, we talked about way back in unit number 1 that glucose is your cell's favorite food. We store glucose inside muscle cells as something called glycogen, so I can store a bunch of it so that it's available for me when I need it. So if you are a glycolytic type of muscle, you're going to break up glycogen, or you're going to break up glucose to make your energy. That's what glycolytic means. If you are oxidative, my oxidative types of muscle tissue use the electron transport chain. The electron transport chain. Now, we're not going to go into the nitty-gritty specifics of how the electron transport chain works in our class. You might do that in your general biology class, but there's a couple of big picture things we need to know about the electron transport chain. So the first thing we need to know about the electron transport chain is where it's found in a cell. Do we know where we find the electron transport chain? Where are these proteins found in a cell? Yeah, so the electron transport chain is found inside those organelles called the mitochondria. Remember those ones that in high school they were the powerhouse of the cell, mitochondria. So the first thing to know is if you are a type of oxidative muscle tissue, you use mitochondria to make your energy, because the mitochondria are the place where we have the electron transport chain. The other thing we need to know, if you are a oxidative type of tissue, this one should be kind of apparent to us here. Oxidative types of tissue use oxygen to make ATP. So we are oxidative, which means I need to have oxygen for this process to work. That's because at the end of the electron transport chain, the way we get rid of electrons that don't have energy for us anymore, we actually give them to oxygen. We spit them out and make oxygen have them. So if you are an oxidative type of muscle tissue, you can't make ATP unless you've got oxygen. If you're a glycolytic type of tissue, you don't actually need oxygen. You're just chopping up glycogen, or you're just using sugar to make your ATP. So that's a benefit for you if you're a type of glycolytic muscle tissue. You don't need oxygen to do your job. Whether or not we've got it, I can still make ATP. But here's the disadvantage if you're not using oxygen to make your ATP. If I'm a type of glycolytic muscle tissue, I have to have glycogen as my beginning point for building ATP. So I can only build as much ATP as I have stored sugar. Once I run out of what I had stored, there's no more ATP for me. If I chop through all my glycogen, I can't chop anything else up. That's the end of the road for me. Compare that to the electron transport chain. The electron transport chain needs oxygen to work. So it's not a done deal. It takes oxygen for it to happen. You have to be breathing. But as long as you have oxygen, the electron transport chain will make tons and tons of ATP. So think about oxidative types of muscle tissue, kind of like they've got a whole forest of trees. There's a ton of wood out there. It's going to take me a little bit longer to go through and chop that up to make it firewood that I could use in my fireplace. But as long as I can keep chopping, I've got an unlimited fuel source. Compared to using glycolysis, if I'm a glycolytic fiber, I've got a pile of firewood that's ready right away for me to chop up. But as soon as that pile's gone, I can't make any more energy. So the second part of the names of these muscle tissues tells you whether they either chop up sugar to make energy or whether they're using the electron transport chain, which requires oxygen to build that energy. Now, we just talked about energy sources. What we have to do, big picture, with our type of muscle tissue, we have to not only consider how they build their energy, but also how quickly they use their energy to give us some ideas about these types of tissues. So here, let me get a blank whiteboard, and we're going to do this together here. I'll put my names across the top here. We've got fast glycolytic muscle tissue. We've got fast oxidative muscle tissue. And we've got slow oxidative muscle tissue. We'll add the full name on that one. Okay, this, by the way, this table I'm building right now, if you haven't already pulled out a piece of paper to start building this with me, here's your wink, wink, nudge, nudge. We really should probably build this table together because it's going to be a really great study tool. So wink, wink, nudge, nudge. First thing we're going to put on our table to fill in our table. Fanshan's like, I was already on it. Look at you. You're learning, right? Learning from how Dr. Alice does things. Okay, so the first thing we're going to put on our table, how quickly ATP is used. And this one should be real easy for us to fill that one in. How quickly ATP is used. The next thing we're going to put on here is how strong the contraction is. How strong the contraction is. Next, we're going to put how we make ATP. And then we're going to add how quickly we run out of ATP. See, this is where we're kind of ultimately going with these words in the names of the muscle tissue. We want to know, when you talk about muscle fatigue, how quickly a muscle is going to run out of ATP. We've got to have ATP to do contraction. If you run out of ATP, you are fatigued. You can't do your stuff anymore. So let's go through and we're going to fill in our table together here. Let me scoot this over. Okay. So my first category, how quickly we chop up ATP, or how quickly we use it. For my first two types of muscle tissue, not a trick question. How quickly do they chop up ATP? Are they a fast or slow lumberjack? Yeah, exactly. Like I said, not a trick question. These are fast ATPases. I'll put that in parentheses here. These types of muscle tissue have a fast ATPase. They are able to chop up ATP really quickly. When I talk about my friend over here, that's slow oxidative. Slow oxidative then is going to be slow, right? This is going to be a slow ATPase. Again, this is that one who's the Instagram lumberjack that's stopping every 2 seconds to take a picture. Do I have any fans of the TV show Schitt's Creek? I just started watching it, and I think about Instagram lumberjack, and it totally strikes me as the daughter. So I don't know if anyone actually watches that show or if I'm just behind the times, but this is my Instagram lumberjack over here, kind of like the daughter in the show Schitt's Creek. So fun times. All right. If we are a fast ATPase, if we're chopping up our ATP really fast, does that give us a strong contraction or a weak contraction? If I chop up my ATP really quickly, yeah, exactly. Kira's chiming in. When we talk about a fast ATPase, that's going to make a strong muscle contraction, or that's going to help you do a big important task. When we talk about slow oxidative muscle tissue, like we said before, that's going to be a weaker muscle contraction, weaker. It's still going to cause movement. It's still going to do stuff in your body, but it's not going to be anywhere near the strength of what we're seeing with these fast ones here. When we talk about the way that you make ATP, if I am a glycolytic type of muscle tissue, what did we say that we used to make ATP? How does glycolytic make ATP? Yeah, exactly. This is all based on the sugars, right? So we're using glucose stored in the form of glycogen. So we're doing that process called glycolysis. Glycolysis, breaking down glycogen, or breaking down our sugars to make energy. I suppose I should add something. Let me add one more column here and we'll fill this in together. How quickly we can make ATP. I didn't specify this before, so I want to make sure to add this to our consideration as well. If I make my ATP using glycolysis, I am chopping up sugar that's already present in my cell. I don't have to make that sugar. I'm not doing anything special with that sugar. I'm just chopping it up. When we talk about a type of muscle tissue that uses glycolysis to make sugar, this is going to mean that they can make ATP really fast, really fast. I've got stored energy and I can chop it up quickly. If you have a muscle contraction that needs to happen really quickly, this is the kind of muscle fiber that can help you out with that, because it's got stored energy sitting around, it's got glycogen, and it's able to chop up that energy really quickly. Yeah, so Kaylin is asking good question. That brings us back to what we have left here in the middle. I have stored sugar that I chop up really fast, but as soon as that stored sugar is gone, I'm out of luck, right? I have nothing left. If I'm glycolytic, I can only make ATP from stored sugar. So when you're talking about a glycolytic muscle tissue, and we talk about how fast it's going to run out of ATP, it's going to run out really quickly. So we'll do that. We are running out of ATP really fast. We fatigue really quickly. Yeah, I like it. Caitlin's saying we crash like a monster, right? We crash like my 4-year-old when she's really tired and all of a sudden the bottom falls out. That's this muscle tissue right here. Going, 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 crash, like fall asleep standing up. That's kind of what's going on with these muscle tissues. So you can use sugar. You've got energy like stored. It's right there. You can chop it up really quickly. But as soon as that stored sugar is gone, you're out of luck. I got no other way to make energy. So fast glycolytic muscle tissues, they're really good for a strong contraction that happens really quickly, but it's not going to last for very long because we have to have stored sugar to be able to do this. Yeah, so Kira is making a great correlation for us. This is the basis of, I don't know if we call it a fad diet or what we'd call it. This is the idea of carb loading. Absolutely. Getting a bunch of extra sugar stored in your muscles, that's going to help out this type of muscle tissue. So the kind that can store extra sugar from your bloodstream, that's these guys, fast glycolytic fibers. So if you carb load, we're storing extra sugar inside this type of muscle tissue. So yeah, that's a great correlation to make. When we talk about our two types of oxidative muscle tissue, does anyone remember what the name was of the thing that we use to make our ATP? What was that process that oxidative muscle tissues use to make ATP? Yeah, exactly. The electron transport chain. The electron transport chain, or ETC. I like it. We'll abbreviate. The electron transport chain. Now, the electron transport chain is basically making energy from scratch. Like it's kind of pulling ATP out of thin air, kind of. That's not totally accurate. Don't quote me on that when you take a test in another class. But when you're thinking about making energy with the electron transport chain, I kind of want you to think about it that way, where like I start with nothing and I make ATP. It's a miracle. It's so exciting. Thinking about it that way helps us to understand why it takes us a little bit longer to make our ATP. We have to kind of wake up our factory, if you will. Yeah, like Elapina mentioned, we've got to get the mitochondria awake. We got to get those machines running. We got to make that ATP. We're starting from level 0, and we got to get up to level 10. We will get there for sure. but it's going to take us a little bit longer because we're not starting with an energy source that's already made. So anytime you're an oxidative type of muscle tissue, it's going to take you a little bit longer to kickstart or make your initial ATP. We're starting our factory that shut down. Once we turn on that factory, remember, the electron transport chain can go forever. As long as I have oxygen, I can make ATP forever. So if I'm willing to wait just a little bit, I can make a ton of energy. That's what my oxidative fibers are doing. When we think about how quickly these types of fibers fatigue, again, this is going to go back to this part of their name, where they're fast or slow. So check this out. Slow oxidative muscle tissue, I have an unlimited supply of ATP, and I break it down slowly. It's my amateur, my Instagram lumberjack here. Slowly chopping up ATP. If I have an unlimited amount and I chop it up slowly, how quickly am I going to run out of ATP? Is it going to be a long time or a short time till I run out of ATP? If I've got an unlimited supply and I chop it up slowly. Yeah, so I'm gonna take forever kind of to run out of ATP, right? So I run out of ATP in a long time. Slow oxidative muscle tissue is the kind of muscle tissue that's really great for endurance, because we have, like I mentioned, kind of an unlimited supply of ATP. So I've got a whole bunch. I've got a forest of trees. I chop those trees slowly. So I'm not going to make a strong muscle contraction, but I can go forever because I've got a forest full of trees and I'm chopping them slowly. I've got energy basically unlimited. So slow oxidative muscle tissue, this is the type of muscle tissue, yeah, like Alapini mentioned, this one's going to be great for marathons, for example, long distance running, activities that are going on for a really long period of time. Even things like keeping your posture, your ability to stay sitting up. We don't think about that a lot, right? But that actually takes a lot of ATP to keep your muscles contracted. So slow oxidative muscle tissue, it's not going to make you a strong contraction. It's not going to move things per se, but it is going to keep going for a long time. When we compare that to fast glycolytic, this is the one that we said ran out of energy really, really fast. But the deal with fast glycolytic muscle tissue is this is the strongest type of contractions you can do. So when you're thinking about doing something like a deadlift, for example, where you bend over and you pick up the heaviest weight you can possibly handle, lift it up over your head and slam it back down. A really fast muscle contraction that doesn't have to last very long, because we're not going to be able to do this very long. If we want to do a really strong contraction and we only have to do it for a little bit of time, fast glycolytic muscle tissue, that's our key. That's the one that's going to be best for that. When we talk about fast oxidative muscle tissue, remember that we still kind of have that almost unlimited amount of ATP that we're making, but we are chopping it up quickly. We've got a fast ATPase. So when we're thinking about how quickly fast oxidative muscle tissue is going to fatigue, it's kind of in the middle. So fast glycolytic, that runs out super quickly, like 5 seconds, you're done. Slow oxidative, that could go for hours. You're running a marathon. Fast oxidative are kind of in this mid zone, if you will. So let me we'll pick a whole new color here. We're going to say a moderate amount of time. I've already used that. I'm running out of colors, man. Moderate amount of time. In the middle, if you will. So really fast fatigue, meaning you can't use it to do stuff for very long. That's over here with the fast glycolytic. Really slow to fatigue. You want to do this forever? That's slow oxidative. Something that we want to do for somewhere in the middle, mainly, here's what I'll say. The biggest difference between fast oxidative and slow oxidative, if I want to do something repeatedly, so more than just once, this one's great for once, glycolytic. If I want to do something more than once, I'm going to need an oxidative fiber to help me do that. I'm going to need a lot of ATP to do that. If I need it to be something that's strong, that I do more than one time, I would use fast oxidative muscle tissue to do that. If it's something that doesn't necessarily have to be a strong contraction, I could do slow oxidative muscle tissue with that. Because remember, oxidative means I make a lot of ATP, and if I'm chopping it up slowly, I can do this forever. I can make a strong contraction though if I take that ATP and I cut it up really quickly. This table that we just made together, underline, highlight, star. Take a picture of it, rewrite it on your own paper. This is the way I want you to think about your types of muscle tissue when you're studying. How quickly do they chop up ATP? Do they make a strong or a weak contraction? Where does that ATP come from? When they build it, do they build it fast or slow? And how fast are they going to run out? When are they going to fatigue? All of these are the kinds of things that we need to make sure that we are able to do when we're working on the homework assignment, and especially when we come to the Unit 3 exam. Let me stop talking for a moment and open the floor for questions. I'm going to check out my chat too, but any new questions? Yeah, so a couple of us are mentioning in the chat, thinking about the sports you're good at, which kinds of muscle you have. Yeah, absolutely. No, it's really true. The kind of muscle tissue you have can 100% dictate what you are best equipped to do. Absolutely. Yeah, and then we're talking about which kind of lumberjack we'd want to have, right, when we had the Great Freeze. Yes, I agree. We want to have, I don't know, for most of us, I think the power came back on eventually. So I might have been rooting for a fast oxidative type of lumberjack for me. Although, man, when my house got really cold, I would have even settled for this one here. Like just a little bit of heat. Just give me just a little bit. Yeah, Lapina's got another reference for the Terminator movie. It's really funny when you start to think about these types of muscle tissue and how you feel when you do exercise and what we see in movies, or the example you have in your notes. Let me go to that slide for us. The different types of activities that we could do in the Olympics, right? So when we're talking about something like a deadlift, where all I need is like 5 seconds of insane power, I want a really strong contraction, which means it's got to be some kind of fast type of tissue. But I don't need that contraction to last very long. So I can use my sugar. Absolutely. I'm going to use glycolytic. So when you're doing a deadlift, like this guy is here, we would use our fast glycolytic muscle fibers to do that. Because fast means it's strong, and glycolytic means only for a short time. Fast glycolytic, that would help me to do that deadlift. And then notice we've got our marathoner, right? If you're doing a marathon, you don't need a lot of energy. It's not that it's necessarily really hard movements, but we need those movements to last forever. So the oxidative part of its name means long time. It lasts a long time. And slow means that it's a weaker contraction. If I don't need something that's as heavy duty as 600 pounds of weight that I'm throwing over my head, if I'm doing a weaker contraction, I can do slow oxidative. And then we can see here in the middle, when we talk about a sport like tennis, tennis is something that is not over in just 5 seconds. Tennis is kind of repeated bursts of strong energy. So when we're doing something like tennis, yeah, we would use our fast oxidative fibers. Fast because we need a strong contraction, and oxidative because we need it repeatedly, more than once, essentially. So as you're thinking about different exercises that you can do, I know there's some examples on the homework assignment, different exercises, what kind of muscle tissue would help the most with them. This is the way I want you to think about it. Is it a strong contraction or is it a weak contraction? Is it a short time or is it a long time? Or, repeatedly being a long time as well. That's the way I want you to think about which types of muscle tissues we would use to do these different things. Hey, let's pull that together with another idea. And that idea is something called myoglobin. Myoglobin. So myoglobin is like the younger brother of hemoglobin. What was the job of hemoglobin? We talked about that back in unit number 1 too. Man, all that unit number 1 stuff coming back to haunt us, right? Yeah, exactly. So hemoglobin in red blood cells is what helps us to transport oxygen. When we're talking about a muscle fiber, muscle fibers don't have this big, huge hemoglobin protein. Instead, they have smaller myoglobin proteins. Hey, remember, myo means muscle. So it's the same kind of protein as hemoglobin, except it's the smaller version called myoglobin. Hey, let's review. When we talk about a protein that has more than one amino acid chain, which level of structure does hemoglobin have? What's the highest level this one goes to? Yeah, exactly. So hemoglobin has quaternary structure. There's more than one protein chain that come together. When I talk about myoglobin, there's only one protein chain. What level does myoglobin go to? Yeah, exactly. Myoglobin only goes to the tertiary structure. It only goes to that third level, right? I've got one chain. It's folded into its 3D shape. That's tertiary structure. Hemoglobin has more than one chain folded together into a big shape. It has quaternary structure. So sorry, there was our protein structure bunny trail, right? Here's what we care about it in this lesson. In this lesson, when we talk about myoglobin, myoglobin does the same thing as hemoglobin. So myoglobin still transports oxygen, just like hemoglobin does. When we think about the kinds of muscle tissues, the types of skeletal muscle that would be most likely to have a lot of myoglobin, which name or which word in their name would mean you'd like to have myoglobin around? Yeah, exactly. Several of us are mentioning if you are an oxidative type of muscle tissue, you're going to want to have a lot of myoglobin because myoglobin is how you get oxygen into your muscle cells. So whether we're talking about fast oxidative or slow oxidative, we're going to have a lot of myoglobin in there. Hey, another thing that the packet asks you to predict, which type of muscle tissues would have a lot of mitochondria? Who's going to have a lot of mitochondria? Which muscle tissue type? Skeletal muscle tissue, I should clarify. Yeah, again, it's those oxidatives, right? My oxidative muscle tissues use oxygen, or they use the electron transport chain to make their ATP. The electron transport chain is found inside mitochondria. So at the very end of your packet, you've got these questions. And this is the last thing we'll do here together as a class. When we think about the different types of muscle tissue, their name gives us an idea of ways that we could help them or ways that we could hurt them. So you just told me on the previous slide, who's got mitochondria? Again, which kind of muscle tissue uses mitochondria to make their ATP? Who's normally got mitochondria? Y'all are like, really? You're gonna make me type it again? I really am. I do love to make you type. Yeah, so if we are oxidative, we use mitochondria to make ATP. We use the electron transport chain. So if we're talking about a type of muscle tissue that I give more mitochondria to, the only one that's going to help are my oxidative muscle tissues, because they're the ones that use mitochondria to build their energy. Same thing down here, right? We just talked about how myoglobin is a protein that carries oxygen. If you're a protein that carries oxygen, I'm going to find you in the type of muscle tissues that are oxidative. If I add more myoglobin to my oxidative muscle tissues, they're going to work even better. And who's going to benefit from having more glycogen? Which kind of muscle fiber benefits from having more glycogen? Yeah, exactly. And hey, with the glycolytic kind, we only have one, right? So stored glycogen, the way I break that down is using glycolysis. So if I give you more glycogen, that's going to help you if the way you make energy is using glycolysis. So for these questions where it asks you to predict, gotta love those predict questions, right? Where it asks you to predict, if I had more mitochondria, who is that going to help? Well, it's basically asking you, who's got mitochondria? Or if I say, I'm giving you more myoglobin, who's that going to help? Well, it's going to help who already has myoglobin and uses oxygen to make their energy. Or same thing here with the glycogen. Who uses glycogen to build their energy? That's those glycolytic types of muscle fibers. So these questions right here at the end of your packet and that table that we built together comparing the different characteristics of our type of muscle tissue, I know we hate it, but that's the, yeah, like Kaylin mentioned, the critical thinking type stuff, the application type stuff. Those are the kind of things that I want you to be able to do when you get to the exam. So make sure, especially when we get closer and we're starting to review for the exam, make sure maybe print out these questions blank again, or make yourself a blank table again, like we filled in class today, to make sure you understand what's going on with our types of muscle tissues. That's all I've got from lesson number 9. We are officially wrapped up. But what questions do we still have about muscle tissue? Or give me a thumbs up. I keep forgetting to give you your daily penguin before like 2/3 of you are gone. So here comes that daily penguin. Maybe bi-weekly. We call it the bi-weekly penguin since I keep forgetting. He's exercising. I'll give him a little weight. Look at that. Kaylin's asking if this lesson was a bad dream. Only you can tell me that. My 4-year-old lately, her thing has been that she keeps saying, I dreamed about that. So like we went to a science museum and we walked in and they had like a dinosaur skeleton and she's like, I dreamed about the dinosaur skeleton. It's like, well, so either she is like really having premonition or she has no idea what that means. I can't tell for sure which it is. I will just, I'll leave it up to debate what it is. It's true. Yeah, Kaylin says, of course, she'd be dreaming about bones. Yeah, I asked her what she wants to do when she grows up, and she told me that she wants to teach her students about bones. But in particular, she wants to teach her students about penguin bones. So coming soon, in about 30 years, you can take a penguin bone class with my daughter. It'll be a party, I'm sure. All right, well, that's all I've got here for lesson number 9. I suspect that we will have 2 sessions next week for lesson number 10. Just based on how long it took us to get through the muscle stuff. I think it'll take us that long with neuron stuff too. So I would suspect we will probably do, what do y'all think? Tuesday, Wednesday, Thursday? Does that work for you all who are here? Otherwise, I can do Wednesday, Thursday, Friday. I'm flexible. Do we want to add Tuesday or Friday? Because we're gonna have to add. I wanna make sure we have enough time. Friday? Okay. I'm getting several votes for Friday. So we will next week, our plan will be Wednesday, Thursday, Friday for class. I will have open office hours on Tuesday. As always, feel free to email me with any questions that you come up with. Don't forget visible body due tonight. And remember, we talked about this. If you're trying to get that temporalis muscle, there is connective tissue on top. So cut off that connective tissue, and then you'll get to temporalis. You'll get full credit for that. So have a great afternoon. I'll stick around for any questions that we have. Otherwise, I'll plan to see you next week.